Hello everyone, this is Ritu Sharma and today I am presenting my project for the course Computer Vision and Image Processing, and the project topic is an analysis of clustering approach for image segmentation. Image segmentation is typically used to locate objects and boundaries like lines, curves in an image. More precisely, image segmentation is the process of assigning a label to every pixel in an image, such the pixel with the same labels share certain characteristics. It is widely used for object recognition, medical imaging, barcode reader, and 3D reconstructions algorithm. And now, moving on to clusters. Clustering, as the name suggests, is the process of organizing objects into groups whose members are similar in some way. The similarity criteria can be, for instance, distance, color, orientation. So, the goal of clustering is to determine the intrinsic grouping in a set of unlabeled data. Clusters can be classified in multiple ways. They can be grouped as monothetic and polythetic on the basis of their goal. They are almost same except for one characteristic. Monothetic cluster members have some common property. However, polythetic cluster members are similar to each other. Another way of classifying is overlap. The grouping of pixels in feature space can be done in different ways. They can be widely classified as hard clustering or soft clustering. Hard clustering is deterministic method, whereas soft clustering is a probabilistic method. Now we will look into hard clustering and soft clustering in details. So for hard clustering, we will discuss k-means. It is one of the simplest unsupervised learning algorithm. The procedure is to classify a given set of data through a certain number of clusters. The main idea is to define k-centroids, one for each cluster. The centroids are then placed far away from each other. In hard clustering, data is divided into distinct clusters, where each data element belongs to exactly one cluster. Now moving on to soft clustering, this algorithm works by assigning membership to each data point corresponding to each cluster center on the basis of distance between the cluster center and the data point. So, more the data is near to the cluster center, more is its membership toward the particular cluster. So, clearly, summation of membership for each data point should be equal to 1. For each iteration, membership and cluster centers are updated according to the given formula. Now we will look into implementation details. The objective of K-main is to segment the data points into classes with the center such that each element has the center with its closest distance. This objective can be optimized by doing two tasks alternatively. First, with the known cluster center, allocate data point such that it belongs to the closest center. Next, with the known allocation for each cluster, compute the center of the each cluster. These two steps are repeated until the algorithm converges. Here, now we will look into the MATLAB code for the implementation. Here we can see that we initialize the input data randomly, and then we have a while loop which calculates the Euclidean distance between each sample and each code word. The loop terminates when we reach the threshold, and threshold is updated over here. Now moving back to the presentation, now we will look into the expectation maximization implementation. So now the given population data, number of classes and some random mean, we have to perform two steps iteratively similar to k-mean algorithm. The first step is the expectation, where the likelihood function is created using the estimated parameter. The next step is maximization, where the parameters are computed to maximize the likelihood function found in the previous step. Similar to the k-mean, the two steps are repeated until there is no significant change. Now, in MATLAB code for the maximization, we can see that firstly we find the distance between the each class over here. We try to find the distance between each class for ground truth and cluster, and then swap the location if the distance is low. This This way, ground truth level matches the cluster label. Again, we run the EM step until the result converges in this while loop here, and the convergence threshold is calculated over here. Threshold is calculated after the ground truth data is compared over here by updating the maximizing the result, because we have to maximize the output. Now, moving back to the presentation, the the K-mean and expectation maximization are implemented using MATLAB for the shown input data. The mosaic image used Gabor filter bank output as the feature vector, and the images were segmentation. Gabor filter implementation can be seen here, where we are smoothing. Here we calculate the Gabor output, and then here we smooth the output, obtaining its absolute value. Now, again, moving back to the presentation. So here the results describe these are the results. Here the result describe the variance of the smoothing kernel. It can be seen that the result is good when the smoothing effect is more. However, further smoothing effect did not help increasing the accuracy because it does not have much feature change. The size of the kernel was chosen as 3 cross 3 in order to make the blurring effect local. This reduces the blurring in the edges between the segment. Whereas in texture classification projects, larger kernel size are chosen so that to average over wide range in the image. The results shown here are for variance of 0.5, and here for the 0.75, and in the previous slide we had it variance of 0.5 and 0.3. So finally, the observation in both K-mean and EM, we can see that both the algorithms are sensitive to initialization. However, K-mean is less sensitive than EM. A set of points were chosen randomly for each class. They were used for both K-mean and EM, and it has been observed that K-mean had a better result than EM. But when the result of K-mean was fed to EM, then the results got much better. This proves that EM is much more sensitive to initialization. As we can see in this graph, in terms of clustering, performance K-mean is very fast, whereas EM is computationally expensive. Since EM builds a Gaussian model for each class, it takes much more time for each iteration. Now we'll see the output generated from the code. As the code execution takes more than 10 minutes, I have already saved the output for both K-mean and EM, and which we will look into right now. So as we can see, this is the EM, this is the K-mean output, and it can be observed that K-mean is less sensitive than EM. So this is K-mean output and this is EM output. So again, if we compare the K-mean and EM output, we can see that K-mean is less sensitive than EM. So also when EM is executed with the results of K-mean, the results got much better. Over here, the results are much better than K-mean. Now, so in the future, Gaussian blur with 3 cross 3 kernel size can be used for blur reduction. This will help to enhance the accuracy of the results. So, thank you, and for any questions or comments, please drop a comment below.